No matter what you're doing, driving, jogging, reading a book, or watching cat videos, there's one thing that all activity has in common. It involves using energy. Sometimes that's simple muscle energy, like the cat jumping. Sometimes it's the cat jumping plus all the energy it took to smelt metals, refine them to electronics grade, and wire them up together into the smartphone you're using to watch the cat jump, and the energy it took to make the machines that made the chips and wires, and the electrical energy powering them then and your phone now. For most of world history, coming up with that energy put a hard fundamental limit on human accomplishment. How much energy you could apply determined what you were able to do. If you were a typical prehistoric peasant, your total available energy was whatever you and your donkey could put in, plus the energy that had gone into making your wooden plow. That pretty much limited you to planting your fields and building a mud hut. But if you were the king, your total available energy was whatever 10,000 peasants and their donkeys could put in, and you got to build things like roads, fortresses, temples, and palaces. You could have gold mined and made into jewelry to plate yourself with and give to your friends. You could have copper and tin mined and made into bronze for your army. You could have exotic spices, perfumes, and foods imported to make your life a bit nicer, all because you had so much more energy to work with. That's a bit simplified, but not very much. For most of history, only the most powerful people in a society had enough physical power at their disposal to do much with. Everybody else had to get along with very little. What made the Industrial Revolution revolutionary was that it put amounts of energy previously reserved for kings and queens into everyone's hands. In 1500 BC, you could harness 30,000 watts of power only by commanding the labor of 200 or 300 people. Today, any 16-year-old driving a small car controls several times that just in direct engine output, to say nothing of the far greater amounts of power embodied in its metals, plastics, and fiberglass. Let's go back in time to see how the possession of astonishing power went from rare to routine. If you took an average Stone Age tribe of foragers, you'd find that each of them used about 6 gigajoules of energy per year, corresponding to about 190 watts of power. Nearly all of that was the energy of getting food and the thermal energy of cooking it. 190 watts isn't enough to do much more than that. Move on to even the most basic farming, and you need a lot more. In New Kingdom Egypt, the typical subsistence farmer needed almost twice as much at 350 watts. He probably didn't expend as much energy walking as the forager, but he would have had hoes, axes, and plows that he or someone else had spent the effort to make from stone, wood, flint, and bone, and maybe a rough wooden cart. He lived in a small mud brick house, and he wore a linen kilt. Making those had taken additional power, and he probably used fire more, harnessing the power of more fuel. That 350 watts doesn't sound like much, but with New Kingdom technology, it would not have been all that easy to come up with, even considering that much of it was embodied in tools and bricks, not exertion. An average worker can supply an amount of energy at a rate that gives about 150 watts of power, but only for short bursts. Sustained all-day work comes out to around 80 watts. This is why one critical boost to agriculture and to civilization was the domestication of draft animals, donkeys, buffaloes, horses, and llamas in various parts of the world. Even the smallest of these can muster as much energy as peak human exertion, and a horse or a mule can work at sustained rates of more than 500 watts, which would wear out most humans in minutes. A few hundred watts of steady power will plow a field, but it won't build a pyramid. That took a lot more, up to 1.1 million watts, according to reasonable calculations, for peak building efforts on the Great Pyramid of Khufu, in addition to sustained base inputs of 30 or 40,000 watts on a routine basis. Construction and maintenance of the Roman road system absorbed a mammoth 350,000 watts each year, And power wasn't just for building. Rowing a trireme took around 20,000 watts during the Roman Empire. And at the time, the only thing that could provide that much power was muscle in massed quantities. Kings conscripted and enslaved laborers by the thousands to transport the armies, mine and smelt the metals, craft the tools and weapons, and haul the materials that built the empires and monuments of the ancient world. Probably for centuries, the straining masses had sought to harness the power of wind and water, the only sources of movement that didn't require muscle. During the classical period, water wheels helped somewhat, but mostly they were just used for milling grain. The largest specimens from the height of Rome's empire could provide about 1,500 watts of power, enough to do the work of 3 or 4 horses or 15 to 20 men. Predictably, the labor freed from turning millstones wasn't saved and allowed to rest, it was promptly redeployed for building more roads and mining more metals. Power needs per person kept rising, averaging about 550 to 650 watts per year in the Roman and Han empires. Less than half of this now went to producing food. Most now provided the power to make tools, weapons, manufactured goods, and the primitive, still muscle powered machinery of the age. But for all that energy investment, material returns were small. All the might of the Roman Empire could produce only enough metal to provide each inhabitant with an average of 2 kilograms of metal every year. And massed muscle remained the only way to get enough power for large energy intensive projects, particularly if they didn't happen to be conveniently located near a river with enough current to turn a water wheel. Windmills, which originated in Persia during the 12th century, weren't much help. Thanks to low and erratic wind power and inefficient designs, most couldn't even produce as much as a single human worker. And that was roughly the state of things up until about the 17th century. The only way to get a large amount of power at your disposal was either to live near a fast running stream and build an array of water wheels, or to be top banana in society and make everyone else work for you. Only then could you get anything done that required lots of energy, like building a road or a palace, producing gold, or a host of other achievements. But by the time the 1600s rolled around, people, especially in Europe, faced a huge problem. For many centuries, the fraction of their energy use that came in the form of heat, for everything from heating food to forging iron, had come almost completely from charcoal. To make that charcoal, their ancestors had deforested large swaths of land, and there was now very little left to burn. The price of wood in major cities, particularly in England, started to rise well beyond the budget of most of the population. Without such fuel, the people of Europe would have had no good options. Giving up charcoal would have meant giving up most bronze and iron tools and most things made with those tools. Common activities would have become difficult or impossible. The standard of living and the level of food production would drop to where they had been several thousand years before, probably leading to an episode of mass starvation and the advent of another Stone Age. So a substitute was needed for the charcoal, but where to find one? Muscles, wind, and water power could move stones and build bridges, but could not provide heat. Biomass, like straw and dried animal dung, could burn to produce heat, but these contained less than half as much energy per kilogram as charcoal. Twice as much would have had to be burned for the same heat output. It wouldn't burn as well, and it probably couldn't get a furnace hot enough to smelt a metal. But the substitute was already at hand. Since about the 1300s, English peasants, too poor to afford charcoal, had been picking up and burning stray lumps of a black material that looked a lot like it. Since they found it floating ashore on the waves, they called it sea coal. Later, when they noticed it in rocks in the hill country, they dropped the first part of the name and just called it coal. Most of it wasn't particularly nice stuff. It gave off such a vile smell when burned that Queen Elizabeth I forbade coal fires anywhere upwind of her, and wherever it was burned, it left everything with a layer of nasty black soot. But coal burning heated homes, food, and people, and in the winter of Northern Europe, that was what counted. It contained almost as much energy per kilogram as charcoal, it was readily portable, and it burned hot enough for smelting and forging metals. By the 16th century, coal was being dug up from pits and hauled to markets all over the land, even though anyone who could afford it still preferred wood. For the first few hundred years, heating was the only use for coal. It displaced the chemical power of charcoal, but did little to relieve aching human and animal muscles. But right around 1700, the curious brains of the Enlightenment discovered how to convert its thermal energy into mechanical power by using it to boil water into a vapor, whose expansion would push stuff around, steam. In 1698, an Englishman named Thomas Savery patented a bulky machine that, when fed coal, boiled water in a confined space, creating a steam vapor that expanded and forced a piston upward, moving a shaft attached to the piston rod. This steam engine was clumsy, inefficient, and failure-prone. Its best output was around 3,000 watts, a bit less than what a contemporary water wheel was capable of, and under half the power that a good Dutch windmill of the time was up to. But unlike the water wheel and the windmill, a steam engine could work anywhere that coal could reach it. Savery's machine finally snapped the age-old link that bound power to muscle. Before then, the only form of power that was both massive and portable was the usually involuntary labor of hundreds to thousands of people, plus or minus animals. Now, there was a machine that could generate power on command, or rather, that could convert the chemical energy of coal into mechanical energy and expend it at a fast rate, i.e., power something. Other inventors were fast on Savery's heels. By the 1730s, one Thomas Newcomen was producing steam engines capable of more than 10,000 watts, and by the end of that century, the steam engines built by James Watt and Matthew Boulton had an average capacity of twice that, the equivalent of about 250 people. The most powerful engine they built was good for 100,000 watts, an output previously available only to anyone in control of 1,000 laborers or a few hundred horses. But their machine was available not only to kings, but to anyone with the money and inclination to buy one, regardless of how many workers, or not, were at his or her command. At first, this almost entirely meant owners and operators of coal mines. Like horses plowing a field for hay, steam engines were first applied to the business of producing fodder for themselves. As forests vanished, English demand for coal had risen so fast that mines drove deeper and were now flooding faster than hand pumps and bucket chains could dewater them. Steam engines, compact and powerful, were the solution. Once they began pumping water out of mines, the coal reached the surface more rapidly than ever before. Energy, which had once cost as much as a life, became cheap. It quickly found further uses. If steam could raise a piston, it could lift the bar of a loom or the weight of a hammer. If it could raise a piston, it could turn a shaft. And if it could turn a shaft, it could rotate a wheel. Steam-powered machinery proliferated. Production of small goods moved from home handicrafts and small shops into large buildings with a drive shaft running along the ceiling, spinning furiously as stokers fed coal into the boilers of the giant steam engine in the basement. A carpenter who had previously turned a lathe by hand could simply loop it onto the drive shaft via a leather belt, and it would spin at a faster and steadier rate. Blacksmiths, who earlier pounded on iron small enough to dent with a sledgehammer, could now hold red-hot ingots weighing tons each under a steam hammer and see them shaped in a minute or two. In these new factories, production of goods soared. Things, from thread to buttons to guns, could now be made in huge numbers, all identical, all interchangeable. It was the beginning of mass manufacturing. Another Englishman, Richard Arkwright, set up the prototype of the modern factory in 1769, and over the next 70 years, sector after sector of British handicraft moved into the factories. Production of things like cloth, for centuries bound to a level determined by the number of workers making it, tripled from 1800 to 1830. Powered by cheap energy generated anywhere on command, goods became more plentiful than ever before. In 1850, steel had been a rarity, with only 8 grams per person around the world. By 1900, there were 18 kilograms per person, with more coming. And as goods became more abundant, they became cheap. They needed to be, for the revolution in industry had also revolutionized work. The artisans of previous centuries had become factory workers, as interchangeable as the spools and rods they now produced. Town craftsmen and country farmers became the urban proletariat, low paid and vulnerable. If prices had stayed as high as they had been in the handicraft era, these workers' wages could hardly have bought anything. As it was, the same revolution that had struck down their old livelihoods had at least put its material goods within their reach. But the new abundance was just as unequally distributed as wealth has always been, ever since the pharaoh could command the energy of 10,000 workers and the peasant the energy of one. Now it was the industrialist and the worker, but it was also the manufacturing nations compared to those that remained agricultural and continued to produce goods by handicraft. Historians call this the Great Divergence, as the economies of nations that took up manufacturing, nearly all of them in Europe, began to experience rapid growth in economic activity and GDP, while everywhere else growth was small and linear if it occurred at all. In industrialized Britain, each person had access to an average of more than 3,000 watts of power every year by 1880. In agrarian traditional China, it was less than a fifth of that at the same time. After a century of this, there would be not only different places in the world, but a first world and a third world. A century of this would also leave the world a little bit warmer. The earliest chemists of the Enlightenment had identified carbon dioxide gas in the 1600s, and in the 1800s, their successors recognized that it had an insulating effect on the Earth's atmosphere. Near the end of the 19th century, chemist Svante Arrhenius predicted that a doubling of atmospheric carbon dioxide concentrations would raise the Earth's surface temperature by about 4 degrees. Writing from his native Sweden, Arrhenius suggested this wasn't a bad thing. We may hope to enjoy ages with more equable and better climates, especially as regards the colder regions of the Earth. By his time, the world was burning more than 1 billion tons of coal each year, virtually all of it in the factories of Europe and America, and the climate had already begun to warm. Today, the annual total is over 10 billion tons, and the warming is not confined to areas that would benefit from it. Throughout the 1800s, the amount of energy at human command kept rising, and the vast majority of it still came from coal. In the middle of the 19th century, the turbine engine was invented. Instead of pushing a piston up and down, the hot steam generated by burning coal would directly spin a rotor and a shaft. In 1888, an average turbine engine could provide 75,000 watts of power. By 1900, the average was 1 million, and the largest engines could manage 30 million watts. Each of them provided many times more power to the users than all the Pharaoh's thousands pulling together. Even the small engine in Henry Ford's Model T car packed more than 15,000 watts, and today the average car delivers almost 200,000. Our daily lives are packed with that kind of energy, most of it now embodied in the cars, computers, and smartphones we take for granted. In the US, our power consumption per capita is about 9,500 watts each year, 50 times as much as the Stone Age forager, 17 times as much as the Roman citizen. A third of that is transportation. We have the power to go where we please because that is what each of us has, power, in greater amounts than anyone in the world could access before today. And even as we seek to draw less of it from coal, we are still enjoying the benefits derived from the one mineral that, centuries ago, first gave ordinary humans access to virtually unlimited power.